Okay, so good morning, everybody. So we have a lot of homework to go over. We'll just go through it in class. So hold on to your homework. Be sure to pass it in at the end of class, but feel free to correct it while we're going over it here. A lot of exercises with divergence and curl, and applying them to some of the fields that we have seen. And also then the last piece of it is a catalog for electrostatics and magnetostatics, so you can see the kind of the common theme that you see in the fields in those cases. Okay, so the first one I'm going to cover today is the worksheet on curl. It's pretty straightforward. You should be able to take these curls. They're pretty simple fields, but there are two of them that I want to cover here in class that just to make sure you understand why they come out the way they do. So they're both, excuse me, that's not right. Both simple fields. One of them is negative y x hat plus x y hat, and there's the solution has, Mr. Byrne, there's solutions up there in front. The solution has a plot of the field, and this clearly has a kind of rotational or circulational characteristic to it, and you can see that and so forth. It looks like this. And if I take the magnitude of u, I see that that is equal to the square root of x squared plus y squared. So this goes like the radius. So the vector field is circulating and increasing in magnitude as you go away from the origin. And this field is clearly defined everywhere. There's no problem with at the origin. For example, the field is not unbounded anywhere on the plane. And then when you calculate the curl of this, you get 2 in the z direction. So it's positive because the circulation is counterclockwise, and it's along the z hat direction because if you put a curl or flow meter in here, you would rotate in that direction. The axle of the curl meter, if you oriented it along the z-axis, it would be in that direction. If you took the curl meter and put it up with the axle, say, along the x-axis, you would get no rotation of the curl meter. If you looked at this field from the side, say from along the x-axis, it would have no rotation. And the 2 there gives you an indication of the strength, the relative rate of rotation. Okay. Now, this is to be compared with this field, which looks exactly like the previous one, except that I'm going to divide by the square of the distance from the origin. It looks like that. And you can see that one, by contrast, it has the same orientation to it. It's still flowing in the counterclockwise direction, but you can see that the magnitude, of course, gets very large near the origin. And so in the plot, I exclude a region here from the plot, because otherwise I can't really make a plot of the function. The magnitude of this then goes like 1 over r. And so it blows up near the origin. Okay, and so it looks like this. It has the same direction of the rotation, but it clearly depends differently on the distance from the origin. Okay, now if we apply the Cartesian form of the curl to this field, we get 0. If you do all of your work correctly. It might be in the z direction, but it turns out to be 0. Okay, which might surprise you. Now the mathematical explanation for it, we'll go over right now. We'll go over right now when we get to one of the homework sets. You'll see there's a physical explanation for this, because this is a field that we see around a line charge or a current carrying wire. The magnetic field looks like this. But let's examine this mathematically. Mathematically, you can see that field should have a circulation someplace. It has a circulation, but it should have a curl someplace in there. And we'll talk about Stokes Theorem, which is, again, further evidence when we look at Stokes Theorem that there should be a curl in here. But the curl in this case is located only at the origin, only at the point in the origin. And there's actually no curl anywhere else here. So there is a circulation but no curl. So circulation but no curl. And when we'll come back, we're going to talk about Stokes Theorem after we do this homework. At the end of class today and the beginning of class Wednesday, we'll examine Stokes Theorem, and Stokes Theorem will help us to understand this mathematically, how it is that it can have a circulation but no curl. Understand that one better. So this is kind of peculiar. This gives you maybe a little bit of a surprising result. And it's very much dependent on this fact that the field, the magnitude of the field drops off like 1 over the distance, which again is like a magnetic field. Remember, when we do a magnetic field around a current carrying a wire, it falls off like this. Any other dependence on the distance for that function, for example, like the one above, where it's proportional to r, will give a curl everywhere. This is a special case. That one special case produces a curl that vanishes everywhere except at the origin. All others would produce a curl somewhere. Yes, sir, Mr.
So
Henry.
if we put a curl meter in it, would it still spin?
No, it wouldn't, even though it might look like it would. And again, the explanation for that will be clearer when we do Stokes Theorem, the mathematical explanation for why that is. If you look carefully here at this field, there's less flow, but over a longer arc length. And on the inside part of the curl meter, there's a stronger flow, but there's less of it. And that has to do with this 1 over r dependence. And so there's an exact cancellation. And another way of, hang on a second, Mr. Bacot. Another way of looking at it is remembering that there's 2 contributions to the curl. There's a contribution where the y component changes along the x direction, and there's also a contribution where the x component changes in the y direction, and those 2 components exactly cancel here. So that's 2 different ways of seeing it. So we'll come back to study this more carefully when we do Stokes Theorem. Mr. Bacot. Oh, I'm sorry. Got to hold on to that. Mr. Dowdle.
So if you put like a closed loop, like anywhere in a function, and you summed all the vectors within the closed loop, would that equal 0?
Yeah, so you wanted me to go ahead and briefly talk about Stokes Theorem, so let's do that real briefly here. In the case of Stokes Theorem, we would take a field, any field W, integrated around the closed loop. Stokes Theorem tells us that this is the integral of the curl of W over that area, where this closed path is the boundary to this surface, and this integral is done over a surface that does not close. It's like for example, you're integrating over a disk, and then the path around it is a circle. That's the boundary to the disk. Okay, and you can see from this example, so this piece, W dot dl, if the field has a circulation to it, W and dl are parallel to each other all the way around. Okay. So this is Stokes Theorem. And then so in all of these cases, we see that this circulation, which would be the integral of W dot dl, will not be 0. But we do have an example of a field where the curl is 0 inside this region, so it must not be 0 everywhere. In fact, it's not 0 in this particular case. It's not 0 exactly at the origin. Okay, and we'll look at this more carefully when we get to discuss Stokes Theorem coming up. Okay, so anyway, so the purpose of this worksheet is simply to practice taking curl and then noticing sometimes there's in a special case, there's a peculiar result that we need to examine more carefully, and we will here. And physically, when we come to the physical example, it will be clearer what's going on. The physical example is easy to understand. Okay. All right, so now let's look at the next worksheet, which is the curl of grad and the div of curl. Again, an exercise in the vector calculus, but this is actually used in application of the Helmholtz theorem and in other cases. So this depends on the following thing, that the mixed partial derivative, which looks like this. This is a second derivative. It's first a partial derivative along x and then a partial derivative along y, and then we do it in the opposite order. We take the derivative along y and then along x. And this can be written shorthand either this way or this way. So this is a second derivative, but unlike the second derivatives that you're used to doing in one dimension, this is a mixed partial derivative. It's called mixed partial. And it turns out that the order of differentiation doesn't matter. And it's easy to see that. For example, the derivative of f, partial derivative of f with respect to x, we would start by taking this difference and dividing by delta x. And then we'll eventually take the limit, but let's hold off on doing the limit first. If we take the partial with respect to y of this thing, we'd have another limit with respect to y, delta y, so we'd have a double, take two limits here. But we would take this is going to be, I'm going to show you what this looks like, but remember this partial derivative here with respect to y is going to be, this partial derivative is a function, and I'm going to evaluate that partial derivative at different values of y. And I take the divide by the difference, delta y. Okay, so putting that all together, you find that you have f of x plus delta x, y plus delta y, minus f of x plus delta x, y minus f of x, y plus delta y, minus f of x, y. You have four terms, and this is all divided by delta x, delta y, and this is the limit. And you take the limit. Delta y goes to 0, delta x goes to 0. Okay, four terms in that thing. Just applying the definition for the derivative in two different directions. And as it turns out, you can see is exactly the same thing as if I had done the partial in the opposite order. I get the same four terms. So the mixed partial is the same either direction, either order. Okay, so we're using that then in the following, then to show that the curl of any gradient is 0. And again, we have to be a little careful here. We have to maybe put on the caveat here that phi is well defined and differentiable, doesn't blow up at this point, right? So we might have to put a caveat here that if phi blows up, is unbounded at some point, then we have to examine this more carefully. All right. So it'd be easy to demonstrate from what we've done here, as long as phi is a well-behaved function. It doesn't blow up at this point or neighboring points and is differentiable. Okay, so that's what I mean by phi is well-behaved. So we'll make that assumption here because when we're doing these things like we found in the case of the curl, where we have a curl, it's 0, except at the origin. You have to be a little careful about those things. So we're going to acknowledge that we've got to be careful in some cases. Okay, but this is a straightforward thing, right? This is, I need to know, to get the curl of this thing, I need to know the components of the gradient. And the components of the gradient, say in the x direction, is just the derivative of phi in the x direction, and so forth. And so when I'm taking the curl, let's look at the curl of phi has terms, for example, in the x direction. It has the derivative with respect to y of the z component of the curl minus the derivative with respect to z of the y component of the z component of the gradient minus the derivative with respect to z of the y component of the gradient, and so forth. The y hat, x hat have a similar structure to them. And so if we look at this here, the phi, the z component of the gradient, of course, is just a derivative with respect to z, and the y component of the gradient is the derivative with respect to y. And so you can see here, this is in fact the difference in the partial derivatives, which we demonstrated is 0. So therefore the curl of the gradient is 0 for any well-behaved function. you can kind of understand that because remember what the gradient does. If we have a function, we have contours of that function like this, for example. Remember how the gradient looks? In this case, it points perpendicular to the contour in the direction of increasing function, like this. And that sort of function, that sort of gradient, that sort of vector field can't circulate. It would be like analogous. You could kind of imagine a situation where you have fluid flow, and the flow is maybe downhill on you have a topographic map, and you have rain coming down, and you get water flowing down the slope, straight down the slope, and that sort of thing can't circulate. There can't be any circulation. It's just going to flow straight downhill. Okay. Now the other one is just a little bit more challenging, is the divergence of the curl of any vector field. The zero again, W must be well behaved. Doesn't blow up. Its derivatives are all defined, at least to the second derivative. And again, this is just a matter of keeping track of components. So we want the derivative with respect to x of the x component. That's one contribution to the divergence. And the x component of this curl is going to be the derivative of, with respect to y, of the z component of w, and subtract off the derivative with respect to z of the y component. Okay, now this one is just produces two terms. The y and z parts of the divergence will also produce each two terms, so we have a total of 6 terms. And you'll find every term here has a partner someplace that it cancels with, so that this term will have a partner in the y component in this piece. We'll go ahead and write it down. Here it is, right there. Okay, that one will cancel with this one. Well, okay, including the derivative with respect to y. So you have 6 terms, and each one has a partner that it cancels with. So therefore, you can see that the divergence of a curl is always 0. And again, that says if you have a circulating function, then it's not going to diverge. Remember, so this is, again, reinforcing what we learned from the Helmholtz theorem, that I can decompose fields into diverging, a part that doesn't diverge and a part that doesn't curl. Okay. But for the time being, mostly what I'm wanting you to get out of this is an exercise in handling the tools, right? These are powerful tools. You just need to learn how to handle them with precision. It takes a lot of practice to not get swamped by all these terms and directions and keeping the x-hats and all that stuff sorted. So it's good practice for that. Everybody okay on that? All right. Good. Okay, so now let's look at the electric field and the magnetic field in the line case, in the linear geometry. So in one case, we have the electric field around the line charge. So the line charge is along the z-axis. And the electric field then we found was 2 lambda times x hat plus y hat over x squared plus y squared. So the strength of the electric field is 2 lambda over the distance from the line, and it points radially out. Mr. McCall.
Where does the 2 come from?
Am I remembering it incorrectly? No.
No. They tried to explain it in the book, and I just.
Well, let's see. I mean, you can go back to Gauss's law. I mean, there's 2 different ways we've done it. One is to do Gauss's law, construct a cylinder around the wire, and then you get, in that case, you get a factor of 2 that comes out between the 2 pi and the 4 pi. Remember, there's 4 pi times the charge enclosed from Gauss's law, and you get 2 pi when you're doing the integral around the surface. So that's where that factor of 2 comes from. The other way to do it, we did a line integral to construct this thing, and you get a factor of 2 as well. Okay, the magnetic field around a current carrying wire looks very similar, except it circulates. So it's pointing tangentially. And the strength of this magnetic field, again, falls off like 1 over the distance. And then there's this, so it's very similar, except it has the current in the wire and the factor C. This is in CGS units. Okay, and now you're to examine these cases. I want you to calculate the divergence and the curl of these fields and see what they give here. And again, we're doing this with the Cartesian form of the del operator. And so that leaves open the question of if these fields diverge at some point like the origin. Both of these fields become unbounded at the origin. And so we can't say that we can calculate the divergence and the curl using the Cartesian form. We have to be a little more subtle about calculating that at the origin. Okay, so we should find that the curl of E and the divergence of B are quite simple. What should those be?
0.
Yes. Why is that? Remember Maxwell's equations. The second and third Maxwell's equations. The magnetic field never diverges anywhere at any time. We're going to find that that's always the case, even when we relax these conditions that we placed on it, like electrostatics and magnetostatics. And the curl of E is 0 in the electrostatics case. That will be relaxed later. But in the electrostatics case, the electric field never curls. Okay, but we'll also find, rather surprisingly, that the electric field and the magnetic fields both have no divergence. And there we have to pause to figure out what that means. And here's where we get now to a more physical explanation of that result. So let's plot the electric field around the current carrying wire, around the line charge. And the field drops off, it points radially outward and drops off. And we're saying that thing has no divergence, and that's rather surprising, right? Really, it has no divergence away from the origin. Remember, the divergence of the electric field is 4 pi times the charge density. And for the line charge, there's no charge anywhere except along the z-axis. Rho is equal to 0 everywhere except along the z-axis. And so we should not get a divergence of E except where x equals y equals 0. Okay, and you can see there that we have a problem with calculating the divergence in the curl for a field that blows up at the origin. So that's something you have to be aware of and watch out for. Now there's a physical explanation of this. Using Gauss's law, it's a little easier to see why that result comes out. Let's go back to Gauss's law, and let's construct a Gaussian surface around this line charge. Here's the line charge, and the Gaussian surface is a cylinder with axis along z. In other words, it's coaxial with the line charge. And remember, we've done this before. The electric field points radially outward, and we apply Gauss's law to this. There's no flux out of the end caps of the cylinder. Remember, there's 2 end caps here that are they're perpendicular to the z-axis. So here's the line charge. Here's the cylinder that we're drawing. We have 2 end caps. There's no flux out of the end caps. So Gauss's law would be if I integrate the flux, if I find the flux of the electric field around this surface, which completely encloses a volume, that this is going to be 4 pi times the charge enclosed. And this integral around the complete surface can be broken up because an integral is a sum. I can break it up into pieces. So left end cap plus the belt plus the right end cap. And then in the case of the end caps, the electric field is perpendicular to the surface area in both of these cases. Surface area elements there. And so there's no flux through the end caps. And so I'm just looking at the flux through the belt. And in that case, again on the belt, I should say E is parallel to dA all the way around. And so E dot dA is just this, and E, the magnitude of E is constant, uniform over the belt. So that says then that the flux, I'm reminding you of this, we've done this before, the flux is just E times the area of the cylinder, the belt, which is 2 pi r times the radius of the cylinder times the length of the cylinder. Okay? All right. Now, and then we found that the charge enclosed, in this case, was proportional to the length of the cylinder, and this little piece, this combination is called lambda. And so we have then 2 pi E 2 pi times the distance, the radius times the length is equal to 4 pi times the charge enclosed. The length of the cylinder drops out, and here you go, Mr. Bicot, there's the factor 2. That's one way to get it. Okay, now notice that this falls off like 1 over the distance, right? And so, but the right, okay. So when and the flux. Hang on a second here. Using Gauss's law, we see, this is Gauss's theorem, excuse me, this is Gauss's theorem, that flux has to equal the volume integral of the divergence. But we just found for this field that the divergence is 0 except at the origin. So that means that this thing has to blow up at the origin. So this is 0 everywhere except it must be non-zero someplace. In fact, it's so big at the origin that it accounts for all of that divergence. Okay, and the other point I wanted to make about this here is you can see the flux here, this flux that we just calculated. Well, the electric field, this is E times the area. The electric field goes like 2 lambda over d, and the area goes like 2 pi d times L. And you see there's a cancellation. And the electric field drops off just inversely proportional to the distance, but the area increases in proportion. So this flux is independent of the radius of the cylinder. So it doesn't matter how big you make that cylinder, you're always going to capture all of the flux coming out because the charge is at the origin. So it doesn't matter whether the cylinder is one radius or another, you're always capturing all the flux coming out. And that shows then why it is that this field that we're looking at, this special case, falls off like 1 over the distance. Right? That's that thing, because it exactly cancels. And so you always capture all of the flux, regardless of how big the cylinder is. The same thing holds for the point charge. The electric field falls off like 1 over distance squared, but the area increases like the distance squared. So the flux around the point charge is captured by any sphere that encloses that point. So it's the same argument, just in a different configuration, different geometry. Okay, now and as I said, when we go over Stokes theorem, we'll see there's something very much like this for the magnetic field. It's very similar when we come back to the magnetic field here. So this was the surprising result. These hold only for x and y, not both equal to 0. Okay, in other words, away from the origin. And we find out really from this argument using Gauss's law or Stokes theorem that those things actually can't be zero everywhere. They have to be non-zero someplace, which is right on the, in this case, right on the line. Yes, sir, Mr. Dowd.
So for the origin, you mean the line itself?
Yes, sir. That's right. Right on. In other words, these are offline, not on the line, off of the z-axis. Anywhere on the z-axis, they'll diverge and be quite large. But right on this, away from the z-axis, they must be zero because there's no charge out there. There's no current density out there. Okay, so that's a gotcha. You just have to be kind of careful about recognizing that. It might throw you off otherwise. Any questions about that? And as I said, we'll do Stokes theorem here, either at the end of class today or at the beginning of class, where we'll do something analogous to Stokes theorem, which we did here. We use Gauss's law around this line charge. We'll do Stokes theorem, apply it to the magnetic field around a current carrying wire. It's a very similar looking argument. Okay, now well, in fact, maybe we'll do that right now. The last one is, I think, is going to be familiar. You're just making a catalog of all these different electric and magnetic fields and phi fields and A fields. And so you're all these different kinds of geometries. So you should have the only thing that's new that we haven't covered specifically in class was the circular loop, the A field and the B field from the circular loop, and that you can get straight out of the book. He calculates that in the far field. So that's the dipole field. In other words, the circular loop produces a magnetic dipole field. It's analogous to an electrostatic dipole field. And we'll talk about that next week. We'll come back and examine dipole fields next week after the test. But I wanted you to include that in your catalog. Okay, so there are lots of geometries, and it's merely a matter of collecting these things. We've worked out these things specifically in many cases, and you can construct some complicated cases from some of the simple geometries. Okay, any questions about that? Okay, so let's go to Stokes theorem. Let's go back and consider Stokes theorem. So it's analogous to Gauss's theorem. Stokes theorem is a kind of two-dimensional version of something that might look like a three-dimensional thing that Gauss's law is. Gauss's law has a volume that's encased by a surface. You calculate the flux coming out of the surface, and that should be related to the divergence, all of the sum of the divergence inside. Stokes theorem takes an area, and for simplicity, let's consider that the area is flat. This is a disk, and so S is the surface of that disk. And again, the surface, this flat disk, defines plane. It's in a plane. And so we have little area elements in this surface. dA, ooh, that's lousy S. We have little area elements here. And those are vectors, so the magnitude is just how big that little plate is, that little tile. How big is that tile? And the direction is up to you whether you pick up or down. Normally we would pick by the right-hand rule, but there may not be a clear definition here of what would be right-handed. So we would pick an orientation for this. So let's pick up for the purposes of this. So dA points out of the page towards you, and that's the direction, and the magnitude is just a little piece of area. Okay, and now we're going to calculate take the curl of W inside of that area, right at that area, and we'll add that all up over the surface of this plate, this disk, whatever it is. So we add up all of the curls, and that's going to be equal to looking at a path, summing up a path, and in this case, if A comes out of the page, then the direction of C must be counterclockwise to be consistent with choosing A coming out of the page. And then we have, in this case, a little piece of DL. DL here is tangential to the path and of a little bit of arc length, has that magnitude, and tangential in the sense of being counterclockwise. Okay, and then we examine how is W parallel to DL. And we find that if we add up the amount of W that's parallel to DL all the way around, that gives us an idea of the circulation of W. So I would define this integral as the circulation. The circulation of W around that path. So now if we get a net circulation of W around that path, it's clear that the curl must be non-zero at least somewhere inside. And in the case of the wire, current-carrying wire, we saw we got the circulation of B. Let's look at B dot dl around. Let's put a path, and this is an imaginary path, just like the Gaussian surface was an imaginary surface. This is an imaginary path that's going to be straddling a wire. In fact, let's make a circular path that's whose axis, center of the circle is the axis of the wire. It's right on the wire. So I want to calculate B dot dl. And we saw that the magnetic field, remember, is tangential. And it falls off like 2 lambda over c times the radius of that circle, right? So it's the same all the way around, it just changes direction, but the strength is the same all the way around. So B dot dl is, they're both parallel. So this is just B dl. And B is a constant all the way around. The magnitude is the same all the way around, so I can pull it out. Remember, the integral is a sum. I can pull it out. So this is B times the circumference, 2 pi r of that circle. So the circulation of B around a wire is just B times, if I have a circle centered on the wire, then it's just B times the circumference. Okay. Now on that other part, we saw that the curl of B was 0, but it must be non-zero someplace because we have a net circulation. If we plot that field, we get that circulating field, right? And the circulation is non-zero, so it must be, the curl must be non-zero someplace, and it's non-zero right on the wire. Okay. Okay, so now let's look then at, so we have the curl of B dot dl, in this case, is going to be equal to the integral of the curl of B dot dA. And so this is a circle that's straddling the wire, and so this is a disk, and the wire penetrates that disk right at the center of the disk. We saw that the curl of B, remember from Maxwell's fourth equation. Remember what the curl of B is?
4 pi.
Yes, 4 pi
Current over
times the current density. Yes, that's right. There you go. That's Maxwell's fourth equation. And the integral of J dot dA over a surface is the charge enclosed, not the charge, the current enclosed, the current that pierces the disk. And in this case, there's only current at the center of the wire, but this holds generally. So we have two different ways of writing Maxwell's fourth equation using Stokes theorem. This is the integral form, and we have the differential form. So this is the integral form, and this is the differential form of Maxwell's fourth equation. You'll usually see it in the differential form, but you can use Stokes theorem to get it into the integral form. Remember, Maxwell's first equation also had an integral and a differential form. remember Maxwell's first equation, the integral form was the flux over the surface was 4 pi times the charge enclosed in the surface, or the differential form was the divergence of E is 4 pi times rho. So you see there's a very similar parallel using Stokes theorem and Gauss's theorem. There's a parallel between that you can understand between Maxwell's first and Maxwell's fourth equations like this. Okay, so let's go back. Let's continue the use of Stokes theorem. Let's suppose we have a conservative force field. And remember, we said before that a conservative force field was defined as something where the work done was independent of the path. And we found that given that condition, we could write the force as the gradient of a vector, gradient of a scalar, which is the potential energy. And we have a negative sign there because we want to give it the direction downhill. Okay, so remember we said that the work done along any closed path was equal to 0 for a conservative force. That was one of the ways of expressing a conservative force, and that would be for any closed path. Well, let's use Stokes theorem. Stokes theorem, then we could say we could convert that circulation around a path. It's like a circulation. Now, what is the circulation of the force? Well, that's the curl of F dot dA. And if this depends on, and if this is 0 for every path, we can change the shape of the path. Then we can argue. In fact, you can construct that must mean if this is true for all F for all paths C, then the curl of F must be 0, and that this is equivalent to the statement that the net work done around a closed path is 0. So in other words, using Stokes theorem, we can say the condition for a conservative field is that the curl of F is 0. So when we did it before, we said the work around any closed path, net work around any closed path was 0. That's the same thing as saying that the curl of the force field is 0. And again, we have to be careful that there's not any place here where the force blows up, right? You've got to be careful about things like that. But so we had an example of gravity near the surface of the Earth. Does the curl of that equal to 0? It's a constant. So you start taking a derivative of it, and the curl is going to give 0. So definitely the curl of that is 0. No problem. How about the other one? Another one we did was Newton's law of gravity. And so now you should be able to calculate the curl of that, and I would convert this to r over r cubed before I tried to do that. But in fact, you'll find that, I mean, this thing points radially outward, right? So you ought not to be surprised that the curl of this thing would be 0. It should be pretty easy to demonstrate that. Okay, and if the electric field, okay, hang on a second. So I want to do that. So, and in general, we say that the force, if the force is written as the negative gradient of a potential energy, then the curl of that thing recognize that? The curl of a gradient.
0.
It should be 0. You just showed that as long as V is well behaved. This is 0 for any V. Right? So that's kind of one half of the argument that a conservative force should have a potential. If a conservative force does in fact have a potential energy associated with it, then it will. Well, let me back up. Let me say it more clearly. If a force has a potential energy associated with it, then it's a conservative force. Okay, but you can go back the other direction using Stokes theorem to say that all conservative forces have to have a potential energy associated with it. That's actually Helmholtz's theorem. Okay. Okay. All right. So, fair amount to digest. There's a lot of stuff in here. And so, yes, sir.
So a non-conservative force, would that have a curl associated with it?
Yeah, well, that's right. Yes, that's right. It would have to. A non-conservative force, by definition here, there would have to be some curl associated with it. Right.
So think about friction as a non-conservative force.
Yeah.
Since that, like thinking of like kind of moment of inertia as it rotates, there's some kind of circulation that's happening in that process.
Okay, so don't confuse. Okay, so you're thinking of a cylinder that's rolling on a surface without slipping, and we said there was static friction in that case. Right? Excuse me a second. Okay, all right. Now there's an additional difficulty when we consider friction. I mean, there must be something like that, but there's an additional difficulty when we consider friction, and that is there's a velocity dependence, right? And we've only been considering here functions of position alone and not velocity, and so there's an additional complexity because of that, possibly. Like kinetic friction depends on the direction of motion. So you have to be a little careful about that. It's clear that there's a integral around a closed path for friction gives a non-zero result, right? That was clear. Exactly defining the curl of a force field, there has to be a little careful because the force may depend on velocity. There you have to be a little careful because we haven't really been considering that. Other questions? So for homework on Wednesday, you're going to do something very much like what you did with a line charge. So you remember we had a line charge and we constructed phi at the middle of at some distance y above the middle of this line has length L. Q is distributed uniformly. We want to find phi and E. At some point here, y above the middle of the wire. And that's an exact result. And then you made some approximation for the case where L is much larger than y, so to give the result that we're familiar with. You're going to do the same thing now for A and B. There's a similar sort of integral construction. If I have a current flowing in a wire and I want to find A and B, there's an integral construction of A and B, very much like what you did before. It's very similar. For example, and the thing to remember when you're doing this is that if you have a function, a vector function, so let's call it W sub x, which could be a function of x and y, for example. Suppose you had something like this, and you're integrating this along x, for example. Remember, the integral is a sum. And so I can transpose the order. I can do this integral in pieces like this. Oops, that's dx here. And again, the integral is a sum. X hat is a constant direction. It's a common term in the sum, so I can pull it outside of the sum. And this is the simplicity of the Cartesian coordinate system. Remember, when we're taking derivatives, the unit vectors don't change direction, so we just treat those as constants when we're taking derivatives. The same thing is true for the integrals. The unit vectors don't change; they don't depend on the coordinates, and so you can just pull down, factor them outside of the integral. And so this, if you see something, you will see something when you see this sort of thing, and you're wondering, what do I do? I have these vectors, unit vectors inside the integral. What do I do? Well, they're just common factors that pull out of the sum, and so you can convert it to something like this. So you will find the exact expression for A and B as a function of y, and then you will find also the expression, what happens when the line is much longer than y, the distance from the middle. And those are the expressions that we're familiar with A is minus 2I over C y, in this case along the y hat direction. Excuse me, along the, if this is x, that should be x hat here. A points in the direction of the current. And this is true in that limit. But you'll also find the exact expression that's true for any y, because the integral gives that to you. Mr. McComb.
If A points in the direction of the current, was there a negative?
Yeah, that's a very good question. Thank you for asking that question. So I'm going to hold you here just for a second to help to try to answer that question. There's a constant here that I haven't added, which is a huge constant, much bigger than that. So this whole thing is still positive in the x direction. There's a big constant that goes like, oh, excuse me, this is wrong too. This is wrong. Hang on a second. This is log y in the x hat direction. Okay, there's another term that's added to this, which goes like log L. And so the L is much greater than y. So it looks like at first you've got this negative sign there, it's going in the wrong direction, but there's this very big constant that makes it positive. Okay, and you'll find that when you do the integral, you find that constant term. And this has to do with the problem we have of setting a reference point for potentials. Right? The vector potential has the same question coming up as it does the scalar potential. The scalar potential, what is the reference point that we choose for the scalar potential? You have the same problem with the vector potential.